Hello, everybody. My name is Paweł Nowakowski. I'm a Senior Application Scientist at Fischione Instruments. And today we'll talk about large area SEM sample preparation using argon ion milling for industrial applications. So before I start my presentation, please use Q&A for submitting your questions that will be answered at the end of the webinar. And after webinar, if you need any additional information, please contact us at sales@fischione.com. So in today's webinar, we'll talk about the sample preparation, a damage that can be induced during the sample preparation. I will do some introductions, what is argon ion milling, and then talk about importance of large area sample preparation and make you introduction to our model 1062 TrionMill. I would finish the webinar with some examples of large area sample preparation. So as you know, there are many sample preparation techniques. Each of them has its advantages, disadvantages, and limitation. One technique can be better for one application, but might be bad for another application. For example, FIP is very site specific, but it's better situated for cross-section sample preparation for TEM application. Mechanical polishing might sound easy, fast, cost-effective, but it's very user skills dependent and introduce surface damage. As you will see later in the presentation, broad ion beam milling is a good choice for large area bulk sample preparation in planar or cross-section configuration when dotted with accurate instrumentation. So an accurate sample preparation technique does not change material's microstructure by inducing any stress, defects, or deformation, does not change chemical on phase composition. A sample preparation must be artifact-free and preserve native structure of material. So before everything happens, before any analysis, a sample must be extracted and adapted to specific requirements of analytical or microscopic technique. This is typically done by mechanical preparation. Here you have examples. Let me activate the laser. Examples of the sample after cutting and some starting of mechanical polishing. You can see here on the surface a lot of damage, a lot of scratches. So that all of that will affect your sample preparation and your final results of your analytical research. So when speaking about crystalline material, the damage mostly comes from dislocation accumulation from this cutting, grinding, and polishing. As you can see here, you have the native state of the material. We have some grain structure, we have some secondary phase, we have some interface, and during mechanical polishing or even initial cutting, this structure can be completely damaged, the interface can be smeared, the grain can deform, the small precipitate can be rejected from the matrix. As you can see here, they can introduce porosity or just disappear. They will not know that they even exist in your material. They can also start acting as an abrasive and introduce the scratches on your nicely polished surface. So there is the old school rule that tell us that the depth of damage can be as large as 3 times the size of abrasive use in the last polishing step. So, for example, if you use 6 micron diamond paste as a last steps or mechanical polishing, the damage can act very easily 3 microns in depth. So another common sample preparation damage is related to FIB sample preparation, and FIB is widely used in the analytical labs all over the world. And the FIB ions can damage sample structure by introduction of points defect, ion implantation, and surface amorphization. So as you can see here, we have gallium implantation, the spatter atoms, and also the vacuums and displacement created by interaction with high energetic and heavy ions like gallium. For instance, here, and you can see here damage in form of amorphous layer on the silicon, and this is the EM image. So this slide illustrates how sample preparation can alter the material microstructure. As you can see here on austenitic steel example, we observe dynamic stray-induced phase transformation of austenite to martensite. The martensite is in the pink color here. And this is induced by mechanical polishing or by FIB bombardment of the surface, as you can see here, even at low energy, as low as 1 kilo electron volts. So as any technique, the sample preparation techniques have limitations. The first is surface damage. You can very easily introduce scratches, dislocation, creates amorphous layer or ion implantation that alter the native material microstructure. Differential material removal between different phases cause topography or relief, making high-resolution analysis difficult. Sample preparation induced artifacts can obscure or mask critical microstructure details, compromising data and interpretation. Material sensitive is also a problem. We often struggle with soft, porous, or multiphase material, and those with which are beam sensitive. And it's also achieving the large, uniform, and pristine surface is often difficult by using conventional method. So for all that problems at Fischione Instruments, we developed solutions. Those solutions and instrumentations are based on argon ion milling as a final step of sample preparation. So as you can see here, using argon ion beam in a specific conditions, it is possible to remove the damage from any samples by spattering effect, exposing its native structure without any artifacts. So now let's see how it works in practice. So why we want to use argon as an ion milling? So ion milling allows gentle, damage-free sample preparation, but uniform material removal without any surface relief or contamination. It's a versatile technique which works with all materials, types, and geometries, allowing achieving optimal surface quality by precise milling parameters control, which is critical for advanced analytical technique like EBSD, for example. So by ion milling, you can do planar sample preparation or cross-section sample preparation, as you can see here, different geometry. In case of our instruments, we use a standard SEM stub that fits any SEM. And there is no sample transfer between preparation holder and SEM holder. So once the sample is affixed to a stub for preparation, it's ready to go to SEM for observation. So in case of planar milling, the material is removed from the surface atom layer by layer, as you can see here on that cartoon, you can imagine that the argon ion milling is like atomic scale sandblasting. And for the cross-section sample preparation, the sample is mounted behind the protective mask, as you can see here, and everything above the mask, it's milled away, creating a flat and clean cross-section. So the mask protects the sample edge during milling, making this method well situated for applications where preserving the edge is critical, such as investigation of layers, coatings, or semiconductor devices. So argon ion milling can be adapted for any application and material, like in semiconductor industry, metallurgy, in aerospace and automotive sectors, can be used for the materials like ceramics, composites, polymers, papers, or geological materials. So here we have some examples of sample preparation by different technique and then broad argon ion milling. So here we have an flash memory, VIN and tab flash memory, as you can see here. And the sample preparation was attempted by mechanical polishing. So as you can see here, all the structure of the sample is destroyed. We have a lot of scratches and we see practically nothing on that sample. When the same sample prepared by broad argon ion milling, remove all that scratch, all that damage, expose you a nice, beautiful cross-section for failure analysis. In here we have a lithium-ion battery polymer separator that was cut by scissors. So this is very fragile sample, very thin and fragile. There is no technique that can be used to prepare that sample and preserve all that porosity structure. But if you use argon ion milling, you can nicely see that pores, those structures preserved. You can zoom in and do accurate porosity measurements if you need for your research. Another example is that austenitic steel that has the dynamic phase change from austenite to martensite. So if you attempt to mechanically poly an austenitic steel, you would have some martensite on the surface. Sometimes you can even interpret that as a retained martensite or martensite short in your sample, but this is not true. It doesn't exist in your sample. Your steel is austenitic, is 100% austenite. So if you use broad argon ion mill for that sample preparation, you will get 100% of austenite and clean and nice sample. And the same you can observe if you use FIB for your sample preparation, you will get that dynamic phase transformation, the austenite to martensite, and you will ask yourself what happens here. Nothing happens. You will just induce that transformation, is artifact, and you deal only with austenite. If you use argon ion milling and one of our systems, you will get pristine, clear austenite sample after preparation. So what that argon ion milling does for us, for our sample, this is example of application for EBSD, but this is one of the technique that you can use and to evaluate your structure of your materials. So as you can see here, if you use mechanical polishing and you stop, for example, at 1 micron diamond paste, you will have no indexing, no signal, nothing. You will have no EBSD patterns, so you have only damage on the surface, like is described here in the red. After 10 minutes of TrionMill, one of our system, you will get up to 80% of indexing. You will start to distinguish the phases present in your material, but still you will see that damage on the surface from mechanical polishing. You can see a lot of scratches, and on the local misorientation here, you can see only the surface deformation, the surface damage, which is, as you can see here, the EBSD patterns quality is very poor. They are fuzzy. But if you finish your sample preparation using a TrionMill, you will get 90%, 99% of indexing, beautiful maps, beautiful patterns, quality. With if you get some local misorientation that will reflect your native material deformation, which is real for your material, not only the surface deformation, which is easier to distinguish when you look at the results and you see that surface damage from mechanical polishing and the real deformation material. This is easy to see, distinguish the difference between these two sample preparation techniques. So as you can see, the broad argon ion milling technique can give you excellent results in terms of sample preparation. But what are the limitations of that technique? So there is one, the limitation is the area of preparation. So most broad ion beam systems are limited to areas around 3-5 millimeters. And beyond that, achieving consistent high quality surface become difficult due to beam and stage limitation. And that's why we developed model 1062 TrionMill ability to prepare truly large areas well beyond 5 millimeters, which is a game changer for advanced analysis. So, but first, why large area sample preparation is important? Why you need that in your research work? So from large area, you can collect representative data, getting a statistical view of material microstructure, not just localized snapshot. Large area unlock true material behavior, revealing homogeneity and detect hidden heterogeneity in your samples. Large area allows you to fit real-world samples. Many industries like aerospace, automotive, and energy sector requires preparing large samples due to the size of the components, like weld joints or part of the engines. Possibility of getting information from that large area improves failure analysis accuracy and also enables correlative analysis between different analytical techniques available if you're in your lab. So now, why the large area ion milling is challenging? So ion sources have a Gaussian intensity profiles, and that make it that the milling depth over a large area is not uniform. The uniform milling beyond 5 millimeters requires precise movement of the stage or the beam, like stage rocking, rotation, or beam specific rastering patterns that many systems cannot achieve. And also there is the edge effect at large scale. The artifacts and non-uniform milling occur near the edge on the samples. So for all that reason that we explained earlier in the presentation, we developed model 1062 TrionMill, and here it's a specification. So the system is able to create the planar and cross-section sample with very high quality. It's important to say that there is no hardware change between a cross-sectional milling or planar milling. The system is developed for both of them. You just, the way how the sample is sitting on the stub is changed. You will see that later in the presentation. So once you fix the sample on the stub, and this is once again, it is a standard SEM stub that fit any SEM. You are ready for planar or cross-section milling, and that's it. You do nothing else. You can use large range of the energies for the milling from 0.1 to 10 kiloelectronvolts. You can feed the sample and mill effectively the sample up to 50 millimeters in diameter. You have possibility to adjust the ion beam size and position, which is very important. You will see that later in the presentation why. The milling angle you can change from 0 to 10 degrees. You have option to have the cryogenic stage and in situ sample viewing, vacuum, inert gas or cryogenic sample transfer, and there is integrated precise sample height detection. We talk about that later. That make the system automatic. You just put the sample to load log, transfer to the chamber, and the system do all alignment to sample to the milling position for you. So this is the top view of the system, and you can zoom here. You can see the 3 ion sources. You can see the stage. We have the Faraday cap that face each of ion source, and you can measure the beam current if you need. And this is the side view. So as you can see here, you have the load log, you have the main chamber, which is separate from load log by a gate valve, which is here. So the basic manipulation of the system are very easy. As you can see here, you will transfer the sample to the stage, and then stage will be travel up to the milling position, and during that travel there is automatic laser high detection of the sample. Or whatever sample height you will have, the sample height can change from application to application, from sample type to sample type. As long as sample is not higher than 25 millimeters, it's ready to go. You just put it in, the system will detect its height and put it in the right milling position. So now the sample is automatically in the milling position, ready to be prepared. So the sample size, and we have the planar milling and cross-sectional milling. So we use the standard SEM stub, as you can see here, fit any SEM. For the planar, you put your maximum 50 millimeters in diameter sample on that stub, can not excess 25 millimeters in the height, and you are ready to go. For the cross-section, the maximum is 50 by 10 by 4 in thickness, and minimum 3 by 3 by 7, as you can see here. So you have your stub, you have your mask, and a 50 millimeters weight sample affixed behind the mask, ready to be processed. And remember that for the cross-section, we create the cross-section in the center here, where the mask is, and the cross-section will be in the center of the mask. So the user interface is very intuitive, which makes the system very user-friendly. There is basically no training to train on the interface, because it's so intuitive to use. You activate 1 or 3 or 2 ion cells, whichever you want. You set up your milling energy, you set up your focus. So we have ability to change beam size directly from the interface. You will see that later. You set up your milling time. If you have cooling option, you will activate or deactivate the cooling. So cooling is integrated to the system, and there is no any hardware and change. If you have option of cooling, You just pour the liquid nitrogen to the system. You can run a flat or cross section as you will run the system without cooling. You don't have to change any stages. You don't have the cryo stage, and then you have to spend 2 days to exchange the stage and then come back to the normal operation. Also spend 2 days. You just pour liquid nitrogen, run your cryogenic experiment. Then when you're done, you just not put the liquid nitrogen to the dewar and you run your room temperature preparation samples. We have the true focus ion source. As you can see here from the interface, you can directly change the beam size. So you have here the picture of 3 beams at 5 kiloelectronvolts, as you can see here, with maximum focus, 100% focus, and at 0 focus when the beam is narrow and nicely spread over a large surface. With that function, you can adapt beam size to your application. So how we make large area milling possible? How we make that this happens? So in most ion mill, a standard ion mill, the beam or the beams looks at one point of the sample. They will focus on one point, or can be center of stage rotation on just one point on the stage if stage doesn't move. And we will mill in that location. 1062 TrionMill was then developed with the flexibility in beam positioning. So we can move this beam around over this 50 millimeters area, 50 millimeter circle, and create a different pattern. So we create different pattern, different beam alignments that allow us to mill different sample size, different area. So here is a special configuration for the very niche application, which is the layering of the semiconductor devices layer by layer. And here we have special beam calibration and beam alignment that allow us to obtain 3 millimeters area with 200 nanometers uniformity. But this is very specific application in semiconductor sector. And for other application like EBSD, SEM, imaging, whatever you want to use on the bulk sample, we have this different alignment, different pattern that allow us to cover any area from very small to 50 millimeters in diameter, and get beautiful sample preparation, as you can see later in the presentation on the next slide already. So here we have example of the titanium alloy. It's 50 millimeters by 7 millimeter sample, as you can see here. So we can see nicely the structure. You have a lot of grains, a lot of microstructure to be investigated. As you can see here, you start to see some big prior titanium beta grains, and inside alpha colonies with this very characteristic Widmanstätten microstructure. So if you zoom in, you will see that very nice, and you can see how during slow cooling the tin retained a beta titanium form in between the grains of the elongated plate of titanium alpha, with very characteristic Burgers orientation relationship, as you can see here, marked on yellow at the phase boundaries. So why a large area is better than a small one? So if you take, for instance, the standard ion milling tool, so you will get something about 5 by 5 millimeters area. So you will barely have one prior beta grain here, so you can eventually evaluate the this grain size as 2.5 millimeters. What is interesting for you is also, of course, the titanium alpha. average grain size. And here from that pretty large 5 millimeter by 5 millimeters large area, you will get your average grain size of 335 microns. Is calculated for almost 2000 grains, which is nice statistic also. But if you will have TrionMill, then you will have 50 millimeters. So you have 10 times more grains. And you can get true average grain size, which is 650 microns, not almost two times bigger than evaluated from the 5 millimeters area. And of course, if you are interested with the alpha beta alpha transformation and prior beta grains, you can calculate their size, average size, and here is calculated from over 30 grains as almost 5 millimeters size, so almost 2 times bigger also. So as you can see here, you can get true grain size from large samples, and a small area will not give you this true answer and true characteristic of your material. Then you can mislead your interpretation and mis-evaluate the application of material. Here, another example of importance of large area is that the large area shows a strong basal and 1120 texture, as you can see here, which are signature of Berger's orientation relationships from alpha to beta transformation. And by contrast, the texture obtained from the small area appears random and fails to capture global texture. So 5 millimeter sounds big, but still you will know in the true texture of your own material in that case. So this highlights why large area sample preparation is critical for accurate microstructure analysis. And the same for the cross section. So you have example here of the standard broad ion beam milled cross section, which is in most cases about 1 millimeters width, as you can see here. But from those that already have one of those mills, you know that you create that characteristic relief here on your cross section from cross-sectional milling, which give you the shadow for EBSD camera. So you can collect the data only from the area like 300 microns. So even if you get the sample, the cross-section wide as 1 millimeter, then this wall, this relief here will make shadow for your analysis, and you cannot truly analyze your microstructure. But however, the TrionMill is allowing you to create cross-section larger than 6 millimeters, as you can see here, showing whole picture of the sample microstructure, revealing the heterogeneity, as you can see here. So look at the microstructure here. We have some similar patterns of this microstructure close to the center, and large grain size in the outer of the edge of the sample, and very fine on one side of the sample. So the microstructure here is is not homogeneous, as you can see here, and this you will never find from the small area sample preparation. So now I will move to air sensitive sample preparation, different sector, the energetical sector, very trendy now, which is lithium-ion battery, of course. So for that, for any air sensitive sample, you need some transfer from preparation to observation. The sample cannot see the ambient atmosphere. So for that application with Corom technology, we develop a capsule that allow us as a vacuum or inert gas or cryogenic sample preparation direct from TrionMill to the SEM. And here we can see an example of the control environmental workflow. So of course, your sample you will load to the vacuum transfer in the glove box using under positive argon pressure, and then you can move your transfer capsule with the sample to our TrionMill, make the sample preparation, and then directly, without passing once again by a glove box, you go to FIB or SEM, which is equipped with the Corom docking station, which is standard in in industry in SEM applications. And so the risk of contamination of your sample is minimized to almost to zero. And there's never zero zero risk, but transfer is very smooth, easy, and once sample is prepared, you can easily and fast go to the SEM for the observation. And this is an example of lithium metal sample. Metal is very reactive, so contaminate and oxidize immediately in contact with air. So if you take the lithium, you do sample preparation, you just go like that to the SEM under air or ambient atmosphere, you will get a lot of contamination. You have surface or oxidation, so a lot of oxygen, as you can see here. This is peak of oxygen, and you have contamination from hydrocarbons, and so big peak from carbon, as you can see here. But if you combine TrionMill with this vacuum transfer system, you will get pristine, very clean sample, no oxidation, no contamination, as you can see here. The oxygen and carbon drops to zero level, as you can observe from this EDS collected at 2 kV, so collected the signal from very surface, so no contamination, nothing. You just can see at low Mach the grain structure of lithium metal, and then if you zoom in, you see only the gray color. What do you see? SEM image of the lithium metal surface. So the application for that is, of course, the development of the lithium-ion batteries. So here we have an example of large cross-section, large 6 millimeters cross-section, and this large cross-section is the NMC cathode. So there is the small particles, and you can count them over that area. You can have over 5,300 particles for robust statistical analysis, and that's what you need in your research. And if you compare that sample preparation to standard 1 millimeter cross-section sample, as you can see here, you can count up maybe 900 NMC particles, which provide limited statistical confidence of your analysis. So, of course, the sample preparation, as you already saw in titanium example, and the sample is uniform, the cross section is uniform. If you go at the edge of the cross section on the center, you have the same quality of sample preparation, as you can see here. If you zoom in, you see nicely the aluminum electrode, and you see here the NMC particles. And of course, you can do any analytical work on that, EDS, to get chemical composition. You can do observation of the individual particles, see grain shapes, grain size. This is bright contrast showing here the nickel segregation close to the center of the particle. And of course, for EBSD, as showed before, you get excellent pattern quality, and you can collect very nice high quality. You can EBSD map, so high quality data that will help you to understand your structure, on develop your structure, your application. You can get very nice statistics because you have large area, so you can accurate calculate your grain size, overall crystallographic orientation, which is texture. With that example, I will finish my presentation and move to the conclusions. Hope I show here that fission instrument TrionMill it's allow you to remove structural damage from mechanical sample preparation and beyond, also FIB and other techniques. Allows large area sample preparation up to 50 millimeters in diameter, which is essential for obtaining accurate grain size, texture, get all that statistical measurement that you wish from your samples. And also supports preparation of challenging sample materials like lithium-ion battery, and allow direct transfer of a sample at a vacuum in inert gas or cryogenic conditions. So you have to remember that as materials and devices become more complex, large area sample preparation isn't just a nice to have, it's essential for understanding material microstructure and properties. So with that last statement, I will finish my presentation. We can move to the Q&A and answer all your questions. And if we don't answer all of them, because time permitted, please contact us at sales@fischione.com. I will now try to this one to go to Q&A. Let me see. Okay, so okay, I'm in Q&A. I see your questions. Let's now answer some of them. So this one, how does your product achieve such high quality large sample preparation? Okay, this is a very nice question, aligned with the webinar. So the key is the broad ion beam and the possibility of beam alignment. So I will maybe come back to that slide very quickly. You will have the visualization, what I'm talking about. So this is the key. The key is our beam and the possibility of the movement around and cover up to 50 millimeters in diameter. So this optimized beam alignment allow us to remove this material up to 50 millimeters in diameter. So as you can see here, the sample is rotating. This is center of rotation. A beam, it's move and different position, creating also the sometimes is crossing each other, that create as call that a hot spot, and then you have the concentrating milling at different spot in your sample, and by sample rotation will remove the material uniformly everywhere. The next question. What's the minimum sample size and thickness the TrionMill can handle, and how does it compare to standard ion beam milling systems? There is the slide showing the sample size. It's here. So the TrionMill can handle sample up to 50 millimeters in diameter for both cross-section and planar milling, which is, as I show, far beyond standard system that is usually between 5, maybe 10 millimeters. In case of the cross-section, we can create up to 7 millimeter cross-section, and please remember that the cross-section will be created at the center of that mask here, even if the system can accept the 50 millimeters large sample. And of course, as I hope I show, that opens you new possibility for preparing real-world samples from like welds, battery sections without cutting them down. So there is, sometimes you don't want to cut your sample because you are afraid to introduce some strain or deformation. You want to have whole vision of the sample without destroy it. So the large sample is critical. Next question. What types of material and applications benefits most from using TrionMill for large area milling? Okay, this is nice question. So what we see is a lot of application for metals like titanium alloy, welded steel joints, also ceramics and composite materials, and those are mostly critical for the application in aerospace and automotive industry. So we have couple of systems out there. It's also very powerful for battery research. When you need to analyze the, the cathode or anode across the wide fields of view. Let me see. We have else. Can you explain why large area EBSD and texture analysis are so important, and how your product makes it possible? So with small area, you only see the tiny spot. It's not representative. You need that large area to have the whole picture of your sample, of your microstructure. So large area preparation lets you capture the true microstructure variation and get statistical data for the analysis like grain size, texture, or orientation, or misorientation if you use a lot of EBSD study. So the TrionMill makes that possible. Oh, that is interesting question. Can you provide some insight on the difference between mechanical polishing damage versus gallium FIB damage? Okay, that is nice. So mechanical polishing tends to introduce dislocation and stray accommodation at the sample surface, which can destroy the microstructure. And in contrast, FIB creates surface amorphization, gallium ion implantation, and atomic vacancies and displacement. These all are due to interaction with the heavy gallium ions at high energy. So for the argon ion milling can easily remove both types of damage, leaving a clean, free, strain-free surface ready for high-resolution analysis or whatever you want to do with your sample in your analytical lab. And okay, so this question follow with another excellent question, this time one of the best. So why argon damage less than gallium in FIB? Oh, so the simplest way to explain it is the implantation. So argon ions doesn't cause the same type of damage as gallium because they are chemically inert, That is first point. And have much lower tendency to implant into the material comparing to the gallium ions. So in the FIB, gallium ions can penetrate the surface, causing amorphization, ion implantation, atom displacement, all that point defects. And argon primarily spatter the material away without reacting with it or embedding itself. So it removes material gently and leaves the surface clean and undamaged. So also in FIB, we use higher ion energy, typically around 30 kiloelectronvolts, which can create significant damage, which is difficult to remove even when you use the lower energy later after you use 30 kV. In contrast, argon, when we use the argon with the for the ion milling, we use the energy around 5 and 6 kiloelectronvolts with possibility of ultra low energy down to 1 kiloelectronvolt or less. And this, as I said, gently spatter, minimize damage, and leaves the clean and artifact-free sample. Okay. I lost my okay, I'm back. I lost my Q&A. So more questions. What is the sample size limitation when you use the transfer capsule for battery-related application? Yes, there is the limitation, but the limitation is not with the system that we limitation is the coming from the port on your SEM. So, and this where the docking station is attached to the SEM. So depending on the port that is available, where it's available, and how the size of the hole in the chamber that you can put through the sample, this is limitation. So it depends on the microscope, and also it is also around that you have the gate valve and the different things. So you have some electronics attached close to that port. So even more shrink that that sample size. So it's there is limitation, but it's depending on the particular SEM that will have to see what kind of SEM you have and what port is available for the docking station. And another question is when you show the image of the mechanically prepared flash memory section earlier, was that cleanup in the flat milling mode or was it prepared as a cross? That was prepared as a cross section. Yes, this image here, can come back to it, or I cannot. Yes, I can. That is cross section mode with the mask. So my mask will be sitting here, and this is what was after milling. So I don't see any new questions coming in. I think I exhausted all of them. So once again, if you have any additional question, I will come back to our contact information. Please contact us at sales@fischione.com. And with that, I will thank you for attention, your time. Bye.